So one more example using population models. In this case, a bird species has a population that is declining exponentially. 5 years ago, the population was 1,400, and today it's only 1,000. So first question is find the value of k if we want to use a population model of this standard form we've been talking about in this section. So a equals a naught e to the kt. And then we'll get into question 2 in a minute. Okay, but so question 1. Now to set this up, I'm going to write up a timeline. So 5 years ago, so this is 5 years ago, the population, so we'll say A, was 1,400. Today, so 5 years later, the population is 1,000. So we need to set up some corresponding values of t. Suppose we set t equal to 0 at this first point in time 5 years ago. Well, then that would mean that today, if we have t measured in years, today t would equal 5. So we're going to start our model at this initial population. So in fact, instead of A, I'm going to call this A0 or A0 for our initial population, 1,400. So then we move 5 years forward in time. So this is when t equals 5. Now the population is 1,000. So if I plug this, well, and this for that matter, into this general population model, A equals initial population times e to the kt. We're wanting to solve for k in this equation, which means we need to plug in values for everything else, for a naught, and for t. So using the information that we have on the chart here. So let's plug in 1,000 for a. That's 5 years later, so k times 5. And we'll use the amount that we had 5 years ago, so the 1,400, as our starting amount. So in this case, t is years since that point 5 years ago, 2015, let's say. Although this example is meant to be timeless, so let's just say 5 years ago. Okay, so we've plugged in information that we're given in the problem. We now want to solve for k. It's nice to pause and think, okay, so am I expecting this k to be positive or negative? Because the population is declining, we're expecting a negative value of k. So that's one way we can kind of check if we've set this up correctly. Now, in solving an exponential equation like this, the first step is to isolate the exponential expression, the e to the k times 5 in this problem. So I'm going to divide both sides by that coefficient 1,400. So that cancels. I'll reduce this. Let's see, the top and bottom here are both divisible by 200. I'm going to divide the top and bottom by 200 to reduce that fraction. So that'll give me 5 over 7 equals e to the k times 5. I'm going to write that as 5k. It always looks nicer with the coefficient, the constant in front. Now to get rid of that exponential expression, we take the inverse operation of both sides, which is natural log. Natural log of this side equals natural log of this side. So natural log of 5/7 equals natural log of e to the 5k, but because of that inverse property, log base e with exponential base e inside of it, that's just equal to 5k. It's just equal to the exponent. And so in order to isolate k, now we can just divide both sides by 5. So in order to find k, you should input into your calculator natural log of 5 divided by 7, close that parentheses, and then divide by 5. And so let's see what you get. Natural log of 5/7 divided by 5. I have negative 0.0673. I'll go to that many decimal places. So it's good. We have that negative value of k, which we expected. And this tells us that this thing is declining by about, if you move the decimal place to the right 2 spaces, it's declining by about 6.73% per year. Okay, so that tells us that our population model, we can plug in what we know here, is, get rid of all this. A equals initial amount, it's not going to fit there, is it? 1400. E to the k, which is negative, what we just found, negative 0.0673 times t. So here now, answer to question 1 is our population model for this bird species. So now I want to get into question 2. Kind of a sad story here, but once the population drops below 100, we're saying the situation is irreversible. That population's not going to be able to recover. When will this happen? So one thing I thought about as I was copying this problem on my whiteboard here, below 100. So I suppose that means that we want to find, okay, so when does it drop below 100, so to 99? I'm going to put 99 for A here. So 99 equals, set it equal to our population model, 0.0673t, and now we want to solve that equation for t, find out when that happens. Any question that's asking you when is asking you to solve for time t. Now, as far as solving these exponential equations, it's very repetitive in section 4.5. So first, isolate the exponential expression, so divide by this coefficient. You've seen this several times before at this point. Now we have the exponential expression by itself. Take natural log of both sides. Natural log of 99 over 1400 equals natural log of that, but when you take the natural log, it's going to get rid of your base e. So if it's okay with you guys, I'm going to go right to the negative 0.0673t. Because when you take natural log of this exponential expression, these are inverse operations, and you end up with just what's called the argument, just what's up in the exponent there. And so now all you have to do is divide by this coefficient of t, which is our k. So divide by k on both sides. Oops, missing a 0. That would be important. All right, put that in the calculator and we'll find out when this bird species is doomed. So 99 over 1400 divide by, oops, our rounded value of k, but that's all right. So about 39 years, it looks like. You should get something around 39.36 is what I get, so around 39 years.